morning, everyone. This is Eric Barron with the Western Interstate Energy Board. Welcome and thank you for attending the first WIREB webinar on a series of webinars on cybersecurity of the electric utility industrial control systems. So with recent news headlines about cyber attacks on companies leading to breaches of customers' personal information and even attacks on utility industries like the events that occurred last year in the Ukraine, this webinar series is not meant to add to this hysteria, but rather help policymakers understand the threat and what is being done to mitigate risks, and ultimately how and what types of public policy should be created. Over the next 3 weeks, we'll be hosting 3 webinars on this topic, which will build on each other, with the final webinar ending with a policy discussion aiming to help state and provincial policymakers in the West build policies that encourage sound cybersecurity practices. This first webinar will provide a brief introduction into industrial control systems and the threats, risks, and future trends for cybersecurity on these systems. Today we have an excellent expert speaker from Veracity Industrial Networks, a tech startup company building a unique platform that creates a unification for industrial network management, control, and cybersecurity in a single pane of glass solution. Veracity is currently working on a U.S. Department of Energy Cyber Energy Delivery Systems project, continuous and autonomous attack surface reduction with SEL and utility partners. Roger Hill, our speaker today, is the founder and chief technology officer at Veracity. He brings 20+ years of industrial control systems experience in many different industrial segments. Before starting Veracity, Roger worked for Siemens as a global head of technology management in their plant security services business. In this role, his department was responsible for the development of key strategic technologies as part of a comprehensive security program for industrial customers. His organization focused on the validation of security controls and penetration testing controls within SCADA security testbed, as well as the development of models to employ within security programs for industrial control systems. In this webinar, Roger will provide an introduction and discuss the differences between electric utility information technology systems and industrial control systems, describe the cyber risks and threats to the electric utility and systems, and walk through and describe the atomy of a potential cyber attack on an electric utility and discuss future trends for securing electric utility systems. Just some quick logistics for today's webinar. We have muted all participants. There will be an opportunity for Q&A from the audience at the end, but if you have questions during the presentation, you can also send questions via the chat box during the webinar and we'll address them when appropriate. With that, I will now turn it over to Roger Hill. Take it away, Roger.
Well, thank you so much for that introduction, Eric, and perhaps more importantly, really appreciate the opportunity to speak to everyone here today on this webinar series. Today, we're going to, let me find my PowerPoint. Okay, so today we're going to really build the foundation for the series. We're going to discuss industrial control systems. What are these systems? We will try not to bore you with too much technical jargon and details. I will say that we rival the U.S. government in our use of acronyms. So I will be very careful not to get caught up in the acronym game. We're going to discuss some of the key differences between information technology systems and operations technology, or OT systems. And these differences have different challenges in securing these systems. Next, we're going to take a look at some of the bad actors, or the adversaries that are attacking these industrial control systems, as well as look at some of the common threat vectors used to attack operations technology. Next, we're going to provide you a unique example, kind of a real-world look at how an attacker could attack these systems, gain that initial foothold, and then move laterally through the network across the systems to achieve their ultimate goal, which is changing the behavior of the control system. And finally, we're going to wrap up our session exploring future trends to securing this OT space and some of the specific steps that are being taken by the U.S. Department of Energy. So without further hesitation, let's just jump right in. So what are industrial control systems? Well, ICS is somewhat of a general term that refers to control systems, or the instrumentation and the visualization that ultimately controls industrial processes. Generally speaking, there's three different categories of control systems. First, there is the discrete controllers. So these are typically small devices that really perform a single purpose, such as a single loop process with an integrated interface. A typical use case here would be for controlling, for temperature control. Next, we have DCS, or distributed control systems. This is designed to control larger production processes for an industrial process. The DCS is comprised of control, instrumentation, and visualization that's all tightly coupled into one cohesive system. The DCS is typically deployed as a much more cost-effective measure for controlling larger processes rather than utilizing many different discrete controllers. Finally, there's a term that you may be familiar with as it's been in the news, and SCADA systems, or supervisory control and data acquisition systems. So SCADA systems visually represent the process that's being controlled. They do this by acquiring the state of the process from the underlying control. So they receive the state from all the different controllers, and this allows the operator to interface with the control of the automation process via visual commands. Pushing a button to start a motor, seeing a feedback that a light is on, for example. So what are the components that make up industrial control systems? As previously mentioned, the SCADA acts as the main operator interface to the production process. SCADA systems are responsible for more than just the visualization of the process, though. They're also responsible for the recording of the process. So, for example, some of your instrumentation, such as temperature values and tank levels, these are recorded for further analysis by the SCADA system. The SCADA also acts as the alarm interface for the production process. This allows the operations to handle problem situations and achieve productivity quickly after a problem. Next are HMIs, or human-machine interfaces. These devices provide local visualization and control by an operator, and they're typically mounted near the machine, or they're controlling line of sight of the equipment that's being actually controlled. Next, we have PLCs, or programmable logic controllers. These are devices that are a very modular architecture that execute a program that actually controls the process. To put this into some very plain language, I'm sure everyone has heard the term the IoT, or Internet of Things. Well, if we think about the industrial Internet of Things, PLCs are the things that tell the things what to do. They turn on motors, and they know when the lights are on by using input and output cards that are physically wired to those actual devices. Within the energy space, you'll also find components such as RTUs, or remote terminal units, relays, and intelligent electronic devices, or IEDs. All of these devices are included in that category of industrial control systems. So where do you find industrial control systems? Well, they're simply everywhere. in virtually every industrial segment. In fact, wherever you might find a physical process that can be automated, you will more than likely find industrial control systems. The PLC, in fact, was invented in the automotive manufacturing industry. The power industry today for the U.S. grid is highly automated. In transportation, you'll find these systems controlling baggage handling at airports. In rail systems, you'll find these systems for subways, ventilation systems for tunnels, as well as for ships and ballast control. The water and wastewater treatment facilities today are highly automated processes and actually have very few human operators at the local site. The chemical sector utilizes DCS, or the distributed control systems, extensively. In fact, building automation today utilizes their own form of control systems for controlling lighting control, heating and cooling, and so on. The key benefits for the utilization are increased productivity and availability. Ultimately, these systems are there to help build products cheaper, quickly, and with greater and consistent quality. In fact, industrial control systems also play a very key role in the safety of the physical process. Let's take a look at industrial control systems from an international standards perspective. A very common approach to defining how information flows through the industrial process was first defined as part of the Purdue manufacturing model. Now, there are many standards that utilize a similar model, but most of the roots all start with the Purdue manufacturing model. So whether you're looking at organizations such as NIST, some of the work done specifically in energy by PNNL, to the international standards, ISO 95 and 99 and the IEC 62443. Many standards utilize these models. Let's just walk through really quickly the different levels that compose these models. So it all starts with level 0, which typically represents the physical process. In this level, this is the actual instrumentation in devices such as robots, conveyor systems and belts and motors and your level transmitters and temperature transmitters. And in level 1, this represents your basic control. This is where you find devices such as PLCs and RTUs and the IEDs. This is the level that is typically controlling the physical process, or level 0. And in level 2, this is commonly referred to as the supervisory or the visualization level. This is where you'll find devices such as HMIs and SCADA. Most commonly, you'll find a level 3.5, which typically represents your industrial DMZ, or demilitarized zone. This really is responsible for creating that physical separation between the industrial process and the business systems. Or you can think of it as this is where the carpet meets the concrete. And level 4 represents the operations, and level 5, the enterprise zones that are providing functions such as ERP, enterprise resource planning, and different supporting functions for that production process. Now, the golden rule of any and all of these models are really, how does information flow between levels? What this typically is that any given level can communicate one level up and one level down, but not share information more than one level. Now, let's take a more specific look at the power sector. When we talk about the power sector, it's very common to divide it into 3 key categories. And this includes power generation, power transmission, and power distribution. The power sector all starts with generation. Generation is primarily hydroelectric and nuclear, with trends now focused more and more on renewables, such as solar and wind. All of these sources, though, combined, make up the power generation category. And from there, power transmission is the bulk movement of power from generation to distribution. So this is the high voltage lines which connect the power generation to the transmission substations. And then we have power distribution, which is really the final stage of power delivery, in which the power is carried from the transmission systems to the actual consumers of the power. Now there are some key fundamental differences in operation security, or OT security, versus information security, or IT security. Perhaps one key difference is the actual goals. A key cornerstone to any information security program is what is known as the CIA triad, or otherwise known as confidentiality, integrity, and availability. This is perhaps one key reason that information security is not directly applicable to the OT space. The priority of goals are essentially reversed. First of all, generally speaking, the priorities of OT is first and foremost safety. And this is closely followed by the availability of the systems. In many of these systems, if you are not producing product, this can have huge financial impacts. And finally, integrity comes in next, followed lastly by confidentiality. Now, a second key difference is what is being protected. Ultimately, for OT, a cyber adversary wants to manipulate the behavior of things. For IT, the data or information is what is being protected. I really cannot stress this difference enough as it relates to the actual impact of an attack. An attack on OT systems can have a physical impact that can have disastrous consequences in terms of health, safety, and environmental concerns. Another key difference is really the skill set. So the skill set that's required to secure and protect OT systems versus IT systems is really quite different. For information security, there are many different security domains that are applicable for a given security program that a security team is focused on. And these are interdisciplinary in many cases. These are things such as access control, telecommunications and network security, information security governance, risk management, software development security, cryptography, business continuity, and disaster recovery planning. For industrial control systems, these same skill sets are still needed. However, there's the addition of having an understanding of the actual automation process, or process engineering disciplines and controls engineering disciplines. The most common approach is the creation of virtual teams that pull individuals from these different silos to work together. For many years, these two silos, IT versus OT, have really been at odds with one another. Well, today, to accomplish our goals, we must bring these two silos together. There's also a distinct difference in the mindset and business objectives between IT and OT. A few of the key mindset differences include the fact that OT technology has developed on a separate yet parallel track to IT technology. Some try to simplify this and state that OT simply lags behind. But the reality is that this is an intentional design based upon the goals that we discussed earlier. The business mission and focus is also different between IT and OT. Another glaring difference is the life cycle, or the refresh cycle, for IT and OT. So, for example, for IT systems, you'll typically see a refresh cycle of every 2 to 3 years, while in OT, these life cycles can be 10 15, even 20 years. Operations personnel are typically thinking about safety. They're concerned with loss of production and quality, the things that they are truly measured on. They're not necessarily convinced that China or Russia are out to get them. Rather, they're concerned with the insider threat. That's not really to say necessarily the malicious insider, but the inadvertent human error, the type of error that impacts safety or the availability of the system. Now, let's look at the IT side of the house. Here, you'll find their thoughts are focused around loss of intellectual property. They're thinking about a cyber breach that can impact their brand image or loss of customer data. These are the primary thoughts in the IT security organizations. Their primary concerns are around advanced persistent threats, organized crime, and sometimes with nation-state actors from China and Russia. There's a linking, though, in terms of the impact, which can have grave consequences for the company, including health, safety, and environmental, as well as mounting financial and legal impacts. And the impact to the company's reputation or the brand image. This is pretty much, there is a news article every week or two of a major breach. Now let's break down some of the categories of these bad actors. First, there's the hacker. They're typically motivated by the thrill, the technical challenge or bragging rights. Hackers are typically not always bad. We sometimes will classify them as white hat, gray hat, or even black hat hackers. Next, we have organized crime, and ultimately they are motivated by financial gain. And the insider threat for OT still represents the greatest threat to these industrial control systems, with over 40% of impacts being attributed to the insider. This includes the non-malicious insider that really results in misconfiguration or misuse of the system. Now, the other side of the coin is the malicious insider, and they are typically motivated by revenge. Then we have hacktivists, such as the group Anonymous. These groups are typically motivated by publicity or a political agenda or even propaganda. And then we have terrorists, which are of course motivated by a desire to destroy, incapacitate, or even undermine confidence in a system. Now let's take a look at some of the common threat vectors. First, sneakernet. Now sneakernet, this is the vector that represents a user walking up to a device and plugging a USB stick into the device and spreading something malicious in that way. Now this was really made quite infamous with the Stuxnet attack that attacked the Iranian centrifuges in Bahrain. Next, there's the mobile devices, which represent a distinct and new threat. For example, an operator could simply have a low battery on their phone and not have their charger with them. And they see an open USB port on the SCADA system, and they simply plug in their phone with really just the motivation of wanting to charge their device. But this represents a vector that can allow malware to propagate from that mobile device to that SCADA system. Wireless is virtually everywhere today, but this has changed quite a bit. We used to conduct site surveys to evaluate the strength of wireless signals to ensure that they didn't go beyond a physical border such as a fence or an outside wall. Well, today with the presence of drones virtually everywhere, we have to think about the threat being three-dimensional. Finally, human error will always be our weakest link, and continuous training is necessary. And finally, we cannot forget about physical security. It's a very common threat vector, especially for industrial control systems, and many of these sites can actually run unmanned or in remote areas. Industrial control systems have utilized what we call a defense in-depth strategy that utilizes a principle of many layers of security. I like to think of the PLC as being the warm, gooey center of the cookie, and the outer rings are the hardened layers. Some of the common measures used to secure OT include hardening of PCs and other industrial devices, utilization of firewalls, employment of whitelisting technologies on devices such as HMIs and SCADAs, use of antivirus technologies, and network segmentation. Now, of course, the real key to securing OT is by conducting a risk assessment. And part of the heart of a security program is really having a strategy around a continual risk assessment strategy. Now let's discuss some of the key challenges faced in securing ICS. First and foremost, there is a lack of visibility of what are the devices connected to these industrial networks, and what is the visibility of the actual conversations taking place machine to machine. We also have key challenges in terms of the legacy infrastructure. As I mentioned, these are long life cycles, and this creates real challenges in the way we do migrations. And in the industrial space, rarely do you see a mass migration. These are typical long life cycles, 4 to 5 year CapEx projects that happen in stages. So what you end up with is a 20-year-old system having to communicate with a brand new system. So that means you're still reliant upon those old legacy vulnerable protocols. We really have a people problem in terms of the lack of subject matter experts in the space as well. And inherently, we have these silos of expertise. So you have your controls engineers and your process engineers. You have IT networking and IT security. It ends up with a situation where it's not necessarily that you have a single person that's just waiting on an alert. As I mentioned, the most common approach here is really with the virtual teams that combines these silos together of IT, security, and engineering. We also have a challenge in that it's almost as if there's a converging event right now. This convergence is happening between this hype, if you will, around the industrial IoT and the promise or the business value to be realized from all of the analytics that can take place on this data from the industrial systems, from predictive maintenance and all of the advantages and so on. Also, there's the cyber events that really is just simply in the news on a daily basis today. These events are just converging to drive change in industrial control systems. Now let's go through an exercise here. We're going to take a look at how would an adversary actually attack an industrial control system. So this is what we call the anatomy of a cyber attack on industrial control systems. Now it starts with an adversary up here in the top left, sitting on the internet. And what this adversary wants to do is to target this industrial control system. Now, that adversary does not have any of the information or IP addresses of these actual devices. And there's some basic security in the system. We have a firewall that's separating the evil internet from our business network, and our business network is separated by our firewall from our process control network. Now, what the attacker is going to do in this example is the attacker is going to take advantage of some common vulnerabilities, in this case with Adobe PDF Reader and Microsoft Windows to exploit the system. Now, if we take a closer look at the firewalls, in this example we have some really basic rules. So the firewall is only allowing the business network to connect to websites in an outgoing way on a couple of different ports, and we're allowing incoming response to only come back as a response from the internet. So that's kind of the current state. So what the adversary is going to do is the adversary is going to send out an email and this is going to be a spear phishing attack to this office user. And if you ever have received a spear phishing attack, it's all around evoking an emotional response, getting you to click on something before you've had a chance to really read it. And that's what this adversary is doing in this example. So this adversary has sent an email with a PDF attachment to this office user. This office user then receives this email, and there's an emotional response that causes that user to click on that attachment. Upon opening that attachment, what it's doing is it's contacting the adversary with something called a reverse TCP attack. And it's basically saying, please give me your bad stuff, which by doing that is allowed to come back as a response through the firewall. And then in the offensive security space, we call this that victim has now been pwned. They've been owned. So that adversary now owns that PC. The next stage is that adversary starts scanning the systems next to that user, that victim, that are connected onto that same network segment, and then utilizes an RPC vulnerability, in this case using a spoof-based attack to compromise and then pwn the adversary. Now, something to note here is that the adversary is not simply sitting outside the internet. When the adversary is attacking the engineering manager, that attack is originating now from the office user. So now that the engineering manager has been compromised, the adversary has scanned the underlying process control network that the engineering manager has access to, and is utilizing a configure-based attack to then send down that exploit to the engineering station and to pwn that engineering station. And then once that adversary has that foothold on the engineering station, it's essentially game over, because that engineering station is responsible for actually programming the SCADA, programming the PLC. So now what the adversary can do is actually issue legitimate commands from the engineering workstation to manipulate the behavior of the underlying PLC system or the underlying physical process, and then can actually disguise what is happening. This is very similar to how Stuxnet actually acted. So hopefully that little step through of the anatomy of a cyber attack was a little bit eye-opening. We have some videos that we did of the actual live system as well. Let's switch gears now and let's start talking about some of the trends for securing these systems. Specifically, let's take a look at some of the approaches by the U.S. Department of Energy. First, if you're not familiar with their CEDS program, this is their Cyber Energy Delivery Systems program. This is a program that's really focused on not just research, but really the R&D and the commercialization of technologies for cybersecurity, but also for resilience. And that's really what the focus will be for one of the trends that we're going to focus on here this afternoon. So really the objective is to enhance the reliability and the resilience of the nation's grid infrastructure through innovation from both academia and the private sector. The scope includes everything within generation, transmission, and distribution, as well as the production and various power storage technologies. Specifically, the Chessmaster project, this is a project that was focused on the continual and autonomous reduction of the cyber attack surface for the cyber energy delivery systems. The unique approach that we're taking here is we're building out a solution that's taking advantage of software-defined networking for the industrial network. Now, this gives us a tremendous advantage because now it is technically impossible to have any device connect to the network without us being the controller knowing about it. Because the underlying Ethernet switches that are responsible for forwarding information do not know how to forward information without the controller providing instructions to do so. That baseline, and I'll promise not to get any more technical than that, provides the foundation of what we're delivering. And we borrowed from some of the DEFCON principles from our military strategy. And that is the principles of defining different threat states. And we're creating a threat state model. So DEFCON 5, for example, is blue sky. There's no known threats. So this would represent a policy for the network that is the most permissive and least restrictive policy. Focus on the business objectives. As we move or transition from DEFCON 5 to the different DEFCON 4 and 3, so a DEFCON 1 in the military is actually nuclear war, right? So we can think of a DEFCON 1 is that we are under a direct targeted attack and have been compromised. So what we're doing is we're defining really a disaster response plan for these different threat states that's pre-designed and pre-tested, that as the threat changes, we can actually execute that response plan. So that under a specific targeted attack, that we can run autonomous zones. And we're ensuring that only mission-critical devices can communicate over mission-critical communications only. So in securing these industrial control systems on this new fabric that really connects all these devices together, it allows us to really implement a new approach to firewalls. We can really think outside the box. So a firewall, if you think back to that Purdue manufacturing level model, a firewall is a policy that executes north to south or south to north. With this new innovative approach, we can now secure communication flows in any direction between any device. It provides 100% visibility of all network devices and communications, as well as, and this is perhaps our most important goal, is abstracting the complexities of the network to really focus on effective and efficient business decisions. And the focus here is really moving towards this trend of task or workflow-based approach, which includes being able to build out a security level model, such as the Purdue model, with simple drag and drop mechanisms, to being able to manage all devices on your network and determine whether those devices should be quarantined or really cordoned off, or whether they're permitted. So the user can easily distinguish what is a legitimate device on my network. An easy approach to creating these security zones. Again, the keyword being usability. And then being able to determine what is authorized communication between these devices. Once they're done with that, of course, now it's focused on the visual validation of the policies they've configured. And finally, having a simple dashboard to understand the progress towards that configuration effort, but also have a simple business glance to understand that they're meeting their business objectives. So in terms of the introductions to threats for industrial control systems, I'd like to provide a summary. So this afternoon, we really tried to build that foundation by providing a high-level overview of industrial control systems, the types of these devices that are used in these systems, as well as perhaps give you a feel for some of the other industrial sectors that utilize these systems. We also discussed some of the unique challenges and differences in securing ICS versus OT. And the focus on the OT systems being on safety, availability, integrity, and finally, confidentiality. We also discussed the risk to attack are really elevated due to these long life cycles and the lack of patching within this space. We discussed an overview of some of the adversaries, some of the motivations of these adversaries, as well as some of the threat vectors that are used. We also briefly discussed some of the future trends and emerging technologies for securing these OT systems. And all of this, like I said, is based on building a foundation to move into our second series and third series within this webinar. And with the next one, we're going to shift gears and really start focusing on resiliency. Specifically, we're going to look at what the U.S. decentralized grid provides in terms of a level of resilience for the grid, but also the underlying protection that's inherent against cyber attacks. We're also going to talk about resilience as a threat mitigation technique. We're going to take another look at the aging workforce problem within the OT space. And what is the connection between this aging workforce problem and the connection to resilience? And then we'll wrap this up by looking at the U.S. Department of Energy chessmaster approach to increasing the overall efficiency of this workforce, but also looking at an approach to improving industrial network resilience. And with that, I'd like to maybe turn it back over to Eric and see if we can't address some audience questions that anyone might have.
Thank you, Roger. That was a great presentation. I think you covered quite a lot of information in a short amount of time. I think that either you you did a very good job at explaining what an industrial control system is, and so with that, I want to allow people to ask any questions. We haven't received any through the chat feature yet, but we do have a manageable number of participants on the call today. So if you'd like to participate verbally, please use the raise hand feature on Ready Talk and we'll address you. You will then need to use *7 to unmute yourself. So I'll give people a few moments to,
So Eric, it looks like we do have a question from Tony, and I'll read the question out loud here. There's been a lot of coverage concerning the Ukrainian grid attack. Are there lessons from that event that are germane to North American system? So, Tony, excellent question. So, there's always lessons learned. I suppose would be my first response. But there's some really important takeaways and others that I don't think are as pertinent to the U.S. grid. First of all, our decentralized control provides an inherent resilience that the Ukraine side didn't necessarily have. And that's one of the things that we're going to dive into a little bit more in our second series. One of the things that really stands out to me, though, that isn't discussed enough in the Ukrainian attack is the fact that the adversary was on those networks for 9 months plus. This is probably the most important takeaway for me personally. And this is where we need to shift our focus. So there's something called the cyber kill chain. You could kind of think of the cyber kill chain as the life cycle or stages of a cyber attack. And it starts with reconnaissance, through exploitation, to the action on objectives and command and control and so forth. The reconnaissance is where we need to focus. We need to discover these adversaries when they're still conducting this reconnaissance stage. This is the single biggest failure in the Ukrainian attack. My personal opinion is what the Ukrainian attack, I think we could have witnessed the world's largest and first lab test on an attack on an energy infrastructure. There's some specific examples where we can see that they actually the attacker made some errors, if you will. But again, my 2 cents.
Thanks, Roger.
If you have a question?
I said thanks, Roger, for addressing Tony's question. I had just a question about what are the challenges with adding complexity to the security systems of these industrial control systems. I mean, I don't know. I feel like making even the system more complex will add to that the challenges with within just the operator itself not being able to function in its own realm.
So it's interesting when we look at the complexity question, Eric, because for a couple of decades, I think we have relied in the industrial side on security by obscurity. And what I mean by that is these systems are inherently extremely complicated and very foreign to IT folks, generally speaking. So that is not a good form of security, as Stuxnet and other examples have really truly demonstrated to us. I think anytime we're looking at any further control that is going to enhance the overall security posture of an industrial system, it's not necessarily a question of the complexity, but does it impact the availability and safety of the system? Because those are very, very important goals and considerations when deciding on these security controls. So I think future technologies cannot negatively impact that availability and safety of the underlying system. I think we have another question from Larry asking what are the tools that China and others are using to infiltrate our government and private sector systems. So I'm going to take a very roundabout approach here, Larry, without getting into specifics. There are many tools available. So it started with quite a few years back with work from Backtrack Linux, which morphed into Kali Linux. There's complete automation suites for performing penetration tests that allow you to perform spear phishing attacks and waterhole attacks and attacking wireless and web servers, all integrated into one complete suite, which really creates an interesting scenario because really it's the script kiddies that can execute these. Virtually anyone can go get a free version of Kali Linux. They can watch a couple of YouTube videos without very much technical competence, and they can start having a negative impact. There's public sites such as Shodan that actually perform scans over the internet of exposed industrial systems. So there's many different tools that are really just either open source or openly available without having to have specially designed tools. Let's see. There's another question of why don't we just use the security tools in place from the IT world? Well, let's take a quick look at that. So, for example, there's a lot of different vulnerability scanning and what we call host and service scanning tools. So some of these tools such as Nmap and Nessus, and these are really some great tools in the IT space. They can provide you a lot of insight of exactly what's on your network, what services are opened, and even what are the vulnerabilities of these systems. Now here's the real challenge that's actually been documented in the industrial context, and that is some of these simple tools such as an Nmap scan that is simply doing an active scan against these IP addresses or devices on the network, and the services have been known to brick ICS devices. Now when I say that, I'm not talking about just bringing that device down, but actually taking it to a state that you cannot recover from. These systems were designed Remember the life cycle a long time ago, and they were not really considering some of the security impacts initially. So the most popular type of an assessment you see in the industrial space is actually done with a clipboard. So it's not that the tools and techniques from IT are even directly relatable. That's why understanding controls engineering and process engineering and the underlying physical process that's being automated is actually quite critical.
Thanks, Roger. Are there any other questions? I'm not hearing any, and I'm not seeing any hands raised. I don't know if I wanted to see if Maury wanted to chime in and if he has any thoughts on today's presentation before we wrap things up. Maury, are you still on? You'll have to press *7 to unmute yourself.
As Maury's doing that, listen, I would just like to thank you, Eric and Maury, for this opportunity, for this webinar and series, and it was great to be able to talk to everyone this afternoon, and I appreciate everyone taking the time out of their very busy schedules to attend this, and I hope everyone got a nugget or two out of it. And look forward to our next series 2 and 3, where we'll dive into some very interesting and expanding material.
Okay, it doesn't look like Maury's going to unmute himself, so we'll just wrap things up here, and I just will say just thank you again, Roger, for the excellent presentation. So next week, on Friday, December 8th, we'll be discussing the resiliency and mitigating the risks of electric utility cyber threat. We'll discuss the improving resilience of the electric utility networks to lead to threat mitigation, and also address some of the challenges with maintaining operations and secure systems, and provide some solutions to simplifying operation decisions. And then in our final webinar, we will address some of the policy challenges associated with cybersecurity. We'll facilitate a discussion of the pros and cons of policy and regulations aimed at improving cybersecurity, and address roadblocks that could lead to more secure and efficient operations. A recording of today's webinar, as well as the slides, will be available within 1 business day on our website. Thank you again for all who participated today, and look forward to continuing this next week. Maury, did you unmute yourself?
I did. I just wanted to say thank you to everybody, and looking forward to webinar number 2.
All right. Great. So with that, we will end today's webinar and look forward to everyone's participation next week. Thanks again, Roger.
Thanks, everyone.